Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So today we're going to little bit change direction. Okay. So before we we move forward, right? Uh, One idea that we have looked at was the idea dealing with we previously looked at magnetostatics, and then we looked at the ideas around um, electric circuits, Kirchhoff's laws, etc. Right? See, now we are going to change direction little bit and look at, instead of magnetostatics, we are now going to look at what is known as um, alternating current. Okay, so I'm going to introduce it slightly differently this time. Okay, the first point I want to make is that when we look at alternating currents, right, we need to understand that there are certain things that go on. Okay, and first we will go over that, but before that I want to introduce you to our two apps. Students who are taking the NEET exam should download Sushruta for NEET. This is for the English students. If you are a Gujarati student, you should take the Gujarati app. And if you're a Hindi student, you must get the Hindi app. Okay. Now, these two apps here are the English version. Okay. For Gujarati and Hindi, we have a combined version. Okay. Now, the Sushruta for NEET is aimed largely at NEET students, and students can get this app also if they want, but this is mainly an English app. Um, the English app is mainly covers physics, chemistry, biology, and is fully indexed to both the IIT PAL, and also we are going to add our own lectures, which are now including this one, which are we have 400, 500 top class lectures that we have done over the last year plus. Okay, so we have a fantastic program. So in addition to Sushruta for NEET, we also have Ramanujan for JE, for the JE students, and you can get these apps. Okay. Now, I'm going to introduce this in a certain different way. Okay. Now, uh, what we are saying is that there is, between the direct current circuits, like that is DC circuits, right, which are where there is a constant battery with a fixed voltage, right? The other form of current is what is called as AC. And AC is a effect that is introduced by what is known as Faraday's law. Okay? Faraday's law states that the induced EMF is uh, proportional to the rate of change of flux, and opposes the rate of change. The direction of the current is always such that it opposes the magnetic field. So what does that mean? It opposes the magnetic field. It is opposite in the magnetic field produced by it opposes this change that produced it. It is a lot like, I don't know if you have heard of Lee Chatelier's principle. That is Lenz's law, right? The direction of current is always such that the magnetic field produced by it is opposes this change that produces it. Okay, so flux is changing, right? And now as the flux changes, and what flux are we talking? We just now looked at magnetostatics, right? B, we looked at two forms of magnetostatics. One is through Biot-Savart's law, and the other is through Ampere's law, right? Ampere's law, B dot di equals B dot dl equals mu 0 I, right? B dot dl over a closed path equals mu naught I, right? Ampere's law. Then Biot-Savart's law, dB equals mu naught by 4 pi I dl cross R by R cubed, right? So these two are the effect of a current producing a field. Now, if that current is changing, okay, or if it is caused by what is known as electromagnetic induction, okay, then the dB changes instance to instance. What does that mean? dB changes. There's a time varying field. Okay? When there is a time varying magnetic field, there is time varying flux. What is flux? Flux is B dot dA. Flux is a scalar, right? Now, that scalar induces a voltage called as EMF, electromagnetic force. EMF is a voltage. So that voltage is proportional to the flux. Okay. So now um, five, E equals N times d phi by dt. N is the number of turns. Okay. So this is a Faraday's law. So this is how we enter into this idea of what is called a sinusoidally changing, if your flux is sinusoidally changing, and we will go back and look at how that flux is going to be sinusoidally changing, it then produces a sinusoidal current. Okay, this is the entry point into AC circuits. Because we did DC circuits, now we are doing AC circuits, and we did magnetostatics in the middle to kind of explain how this leads to this AC circuits. We are then going to take a step back sometime during this lecture, starting this lecture and next lecture, to look at how this is caused. There is another law, which is another aspect of magnetism, which is known as electromagnetic induction. So let me briefly describe this electromagnetic induction, or better still, explain how that happened. Okay, but before I go there, I want to tell you that eventually the current that gets produced is what is called as alternating current. What comes in the wire into your house is alternating current. It is a sine wave that comes into your house. Okay, this current is like that. It is alternating. Why do they say alternating? Because it's the one side is plus for some time, the other side is minus, the other side becomes plus, and this side becomes minus. So it is alternating, plus minus, plus minus, plus minus, plus minus, plus minus. Okay, so because the voltage is sinusoidal and alternating, you can say that it is a voltage which is of the form V sine omega t. Okay, now if you pass it through a resistor, you can think of a electric bulb as a kind of resistor. Okay, what does an electric bulb do? It converts the when you pass it through that tungsten. In the old days, there was tungsten, of course. Now there is all these LED bulbs. You should be using an LED bulb in your home, right? Because it is uses less power. Okay? When you pass it to an LED bulb, what happens is it acts as kind of like a resistor. Tungsten definitely acts like a resistor. It even looks like a resistor. Okay, so what does it do? Right? It typically, when you pass current through a resistor, it absorbs that and converts it to some other form. In the case of the light bulb, it converts it to both heat and light. Okay, that's why you feel a little warmer when the lights are on. Okay, so there is some amount that gets converted to heat, some amount that gets converted to light, and then we all enjoy the light that is produced. Now, now what is the value? You still have Ohm's law, which works, right? V sine omega t is the current, right? Notice the sine omega t, that is, it is time varying. Okay, so n d phi by dt, if phi is time varying, the EMF is also time varying, and therefore that's how you end up with alternating current. So what is the current? Current is also alternating. You just don't see it, that it's alternating. Okay, so now if you had a single resistance circuit, the circuit is in phase. Okay, Now you have what is called a phasor diagram. What does the phasor diagram do, right? Phasor diagram provides a in some ways it tells you, now I have a a voltage, okay, which is at, which is this one. Remember, the operative word in a phasor diagram is phase. Okay. Now notice that if a resistor is just a linear circuit, most of these circuits are linear circuit. Resistor is just a passive circuit. All that it does is it absorbs power, and it absorbs power in phase. Okay. Now, so the current is completely in phase. If this is sine omega t, this is also sine omega t, right? But the capacitor, for instance, 1 by c integral I dt is the voltage, or c dv by dt. Okay. Now, L di by dt is V for an inductor. Okay. For a capacitor, c dv by dt is I. Okay. So when you have that kind of a differentiation, what happens is that the phase is set to change. So if the current, the voltage is a sine omega t, the current will be a cos omega t. In one case, minus cos omega t, the other case, plus cos omega t. Okay. So in one case you integrate, the other case you differentiate. Okay. So one goes forward in the phase, the other goes backward in the phase. So the phasor diagram, when you connect this circuit to a capacitor or a inductor, the phasor diagram will switch to where, let's say, this is A is the V is the, this is the voltage, OA is the VM, right? IM is also along the same line, OC. Okay. But if for a purely resistive circuit, it will be in phase. So that's what they mean in phase. But in a partially resistive circuit where there is also, let's say, an inductance or a capacitance, let's say there is an inductance, you will have the current being like that. It will be in a at an at out of phase with the voltage, because there is a either an inductor or a capacitor. So that is the basis of DC circuits. Okay. So now we don't have there is of course the idea of instantaneous power, which is I square R. Okay. But then typically when you know, because that is also time varying, right? So typically what they do is they calculate average power or root mean square power. Root mean square is what, right? Root mean square is what? Root of I square. Okay. Root of I square is root mean square. Therefore it is Im by root 2, where Im is the maximum, the peak. Im by root 2 will give you the root mean square power. Vm by root 2 will give you the sine square theta, basically, right? Now, the average power is roughly half of IMS squared R will give you the average power. IRMS square times R. I squared R, the RMS square gives you the, okay? So what is the power? V times I, right? And you're looking at the average power. The average power is the power over a cycle, right? So you end up with I square R, where I is the RMS current. RMS current is Im by root 2. And we have, or V times I, VRMS, right? So keep that in mind, right? VRMS by R is IRMS. Okay, keep that in mind. Okay. Simple example. Alternating current 220 100 pi, right? So omega t is what? Omega is what? 100 pi, right? Omega is 100 pi, right? Now, if omega is 100 pi, right? Time taken for the current to rise from half of the peak value to the peak value. What is the peak value? 220. What is half the peak value? 0.5 times is 110, right? If 110 means what? Half the peak. 0.5 equals sine 100 pi t naught. At t naught it is 0.5, right? Now at to the peak value, so at t1 it is 1. So then you look at t naught and t1. So t naught is 1 by 600. T1 equals 1 by 200. So T1 minus T naught is roughly 3.3 seconds. So this is a very straightforward calculation. What are we looking at here? Resistive circuit, resistive load of 50, right? So now what happens to the voltage? Voltage follows a very standard procedure. It just follows the, it is a sinusoid. Current follows the sinusoid. That is the point that they are making. You must understand this figure, what's going on here, right? Now, if on the other hand you had a resistance and a capacitance, or a resistance and an inductance, the if this is a sign, this will not be a sign, rather it will have a plus 5. Okay, and that's why it's called a phasor diagram. The current will be out of phase with the voltage. This is a very, very important idea that you must learn, in when you have to solve problems with alternating current. Okay. So today what I'm going to do in terms of continuation is I'm going to next look briefly also at the idea that we skipped, which is electromagnetic induction. So this is alternating current. So why did we introduce first little bit of alternating current and then come to Faraday's law, is to emphasize the idea of how important this is. Okay. So all of you know Michael Faraday's invention, finally led to a great new understanding of these things, you know, and as a result, today we are all huge beneficiaries of the idea of electricity, right? How do we benefit from the idea of electricity? We benefit from the idea of electricity because it just gets generated and then it shows up at your home. Okay, so we looked at currents in magnetostatics. We looked at currents producing a magnetic field and causing, and the force between currents, I times L cross B, right? Q times V cross B. That the current, if there is a moving charge in a magnetic field, it experiences a force, right? Now we are going to look at the reverse. If there is a changing magnetic field, previously there were not changing magnetic field, there were moving charges. Now there's going to be a changing magnetic field. If there is a time varying magnetic field, in the previous case, there was a charge moving in a magnetic field. What is a moving charge? It's a current, right? Now, a current in a magnetic field experiences a force. I times L cross B, F, because I times Q times V cross B, right? Now, what we are going to have is the opposite. Okay? You have a time varying magnetic field. What does that do? It induces a current. Okay. Now, where do you see see this idea? You see this idea in the generator in your cycle. Previously, there used to be these cycles. They used to have a motor. They used to have a generator. Okay. Generator will be right next to the tire. I don't know if you have seen it. The generator will be right next to the tire. The person is, of course, moving the tire, and while they move the tire, they also move the generator. When they move the generator, What does it do? Generator spins. Okay, when the generator spins, right, it produces a changing magnetic field. There's a electromagnet or a magnet inside that dynamo. Okay, it's called a dynamo. Now, what does that do? It produces a changing magnetic field, time varying magnetic field. When you have a time varying magnetic field, then you have a induced current. So Faraday's experiment on induced currents through, so in 1831, changing current in a coil. So if you have a changing current, right, then um, then it so if you have a changing magnet, right? So moving a magnet, so he had a coil and then he moved a magnet near it. Okay, when he moved the magnet near it, there was a current induced in the coil. Why was there a current induced in the coil? Because that's what Faraday's law states, that there will be a current induced in the coil when there is a changing magnetic field, and this changing magnetic field will cause a input voltage. So what is that voltage? N times. If you have n circuits, n turns, n times d phi by dt. So look at this case. Okay, so now he has a this circuit. Okay, now he is moving up and down. This bar closes the circuit. Okay, now he moves it up and down, up and down, up and down, or he moves the magnet through the induced current, induced coil. So he has a closed coil, moves the magnet up and down into the induced coil. It will produce a current inside the coil. In this case, like they are moving, they have a magnetic field, they are moving the one part of the coil. That can also be done. You can either move the coil or you can move the magnet. Either case, the closed circuit sees a changing magnetic field. When it sees a changing magnetic field, there is current induced in it. N d phi by dt equals V or EMF. EMF equals negative M d phi by dt. The negative is produced by Lenz's law. Okay. Now, what is the field? The field is B dot dA, right? What is the flux? The flux is B dot dA. The field is B. The flux is the B dot dA, where S is the surface over which let's change. So you need a changing magnetic field. It has to be time varying. B dot D has to be time varying. Okay? Therefore, that is Faraday's law. Therefore, and now we all understand the EMF is E dot dl is V, right? dV by dr is E, right? Or dou V by dou R is E, right? Therefore, EMF is E closed integral of E dot dr. So, and therefore, we have, the formula for EMF, right? d phi by dt minus d phi by dt is the induced EMF. Okay, so now, so one when one is asked to find some of these equations, most often you are multiplying n times a times b times like that. Okay, and then you are doing dB by dt or dA by dt. Okay, so you're changing the area. Okay, so and so that's where this is a very very typical way this is done. Okay, and so B is increasing with time. Okay, or B is decreasing. Okay, so sometimes, so when you have alternating current, what happens is when you rotate something, right? In one case, the current is going this way. Let's say you have a constant magnetic and you rotate a closed coil inside it like that. You have a fixed magnetic field like this, in that you're rotating. You have a coil like that and you rotate it, right? So when it's parallel, B dot dA is 0. When it's completely perpendicular, B dot dA is B times A. When it's at an angle, it's BA sine omega t, right? So that causes, so when you're this way, the current is this way. When you're this way, current is the opposite way, right? So when, let's say, you rotate a magnetic field like this, you rotate the circuit. The circuit is like this. You rotate it, right? Now, let's say you had 20 turns. So n times that area that is being covered, n times b dot dA. Okay, and the d by dt of that. Okay, n times b dot dA, the d by dt of that gives you the EMF. So please understand that. So and this is, we will face it in a long over a long time. You face it if you become an electrical engineer. You will face it. You know, if you become any types of engineer, they will make you learn some of these things. And of course, it's very good to know. Okay, learning science is a very good thing. Okay, learning sciences helps you become an expert at learning. Once you become expert at learning, you succeed at learning other things. Okay, so now so the key point here is the flux. Flux is we looked at electric flux, if you remember, E dot dA, right? This is magnetic flux, B dot dA. Okay. So the time varying nature of the flux, d by dt of phi, will give you the EMF. And so that's why you have to move the magnet. One common place where you see this is, I don't know if you have been to like a river Theri Dam in Uttarakhand, Sardar Sarovar Dam in Gujarat or Madhya Pradesh, right? Or Maharashtra, right? Sardar Sarovar, Theri. On the Kaveri, we have the Metu Dam, right? Then we have Nagarjuna Sagar, right? Then we have, other dams, very well known dams, dams in the Godavari, dams in the Krishna, fantastic dams across various parts of India. The Periyar in Kerala, Periyar, you know, so many wonderful dams. India has been a huge beneficiary of these dams. We have not yet built, fully tapped the Himalayan grid, right? This Himalayan grid continues to, be a possibility to be built to generate hydroelectric power for the nation, you know. But as important, right, are thermal generation. Okay, thermal generation is also extremely important. Okay, thermal power, thermal generators, power, and how do they work? They work by making, also producing mechanical rotation. But the power for the mechanical rotation is not falling water, is not the Ganga falling from the sky. It is not the Ganga falling from the sky, falls on the head of Lord Shiva and then down to down all the way to the ocean, right? It's not the Ganga, right? In this case, it is the power that is generated by coal. Okay, coal power, coal when it is burnt moves steam. Steam drives the makes the circuit rotate and also produces they use electromagnetics to produce a electromagnetic field using along with that. So that process is what drives thermal power. Okay, so when there is a changing electromagnetic field, leads to an electric field and then current being induced in the surrounding coil. Basis of the idea of generators and other electrical implements like generators. Okay, so this is the fundamental idea behind Faraday's law. And so, having explained Faraday's law, we will now turn our attention back to electrical circuits. We will come back to Faraday's law, solenoid, and induced EMF examples. We already looked at this before, but I wanted to go over some of these examples. But before that, I wanted to get you all familiar with the idea so that we can proceed forward with, electromagnetic circuits, with the alternating current circuits. Okay, so alternating current circuits, we looked at the phase diagram and the phasors, right? So now the average over one cycle of the power IRMS square R gives you the average power. Okay. Now, if you had just an inductance, a pure inductance connected to a source, you have L di by dt. Okay. Now, the L di by dt will give you the voltage. V minus L di by dt will give you the right. Therefore, you have, if the voltage is sinusoidal, right, the current will be shifted by a phase pi by 2. So pure sinusoidal case, the current will be cos omega t. Cos omega t is one phase lags the with respect to the voltage. If you had similarly a, so in the phasor diagram, if this is the voltage, the current will be 90 degrees behind it. So it is a lagging current. Look at this. Look at this picture. Remember this picture. This is a pure inductance. Okay. So with this picture, you will see a lagging current. So, so this is a very important idea that you should learn to be comfortable with. Okay. So today I'm going to stop a little bit early. Because I want you to understand how these parallel ideas are built. Okay, electricity and magnetism should not be a huge mush of misunderstanding for you. Okay, so previously we were talking magnetostatics. Now we are talking a different idea, which is electromagnetic induction. In electromagnetic induction, what happens is you have a changing magnetic field, time varying magnetic field inducing a current. Previously, there were currents and magnetic fields, and there was force. Now, that's what drove the fan, right? The fan is different from the generator. The generator, a time varying magnetic field induces a current. Generator produces the current that shows up in your house. Generator is somewhere else. It is in a thermal plant somewhere. It gets generated there and it comes to you. You're in one large circuit. Your house is part of a large grid, electric grid, a very large circuit. Okay, and so all these circuits, they pump, and they have transformers everywhere. They transform electricity, and they push the electricity down to your home. Okay, they carry it in load in long thick cables, and they show up in your house. Okay, large number of electrons get created, they go in a circuit, and they go back to where they came from. Okay, so so understand how this law, there's a continuous interplay of these electrons. They are used to produce power, which is then transmitted over long distances into homes all across India and or anywhere in the world. Okay, we all get the same kind of power. They only, in some cases they use coal, other cases they use natural gas. In some cases they also use nuclear. Okay, nuclear is another source. Transform energy into electrical energy. Then you pass it through your wire terminals. All right. So with that, I'm going to stop for today, and we will be re-engaging on these topics in the next class. Okay. With that, I'm going to stop. We'll be re-engaging with these topics in the next class, and then we will continue the discussion on both electromagnetic induction as well as AC circuits, circuits that are the result of Faraday's